Pillar me up, Scotty. When we hear the keyword instant transportation, we frequently consider marvelous advancements that, in a split second, transport matter from one spot to another at the press of a button. Yet, while the fiction displayed to us in Star Trek and so forth is actually inconceivable, quantum instant transportation depicts an interaction that has since a long time ago shown up in actuality exhaustively. We are dealing with the exchange of quantum data, like the spin condition of a particle, which is moved to a far-off second particle. Quantum instant transportation doesn't move matter, but only its stored information. Indeed, scientists have recently succeeded in accomplishing some pivotal achievements in this astonishing field. For example, there are the researchers at the Max Planck Institute for Quantum Optics who have developed a technique that is as simple as it is notable, requiring only a single photon as a transmission asset. Or the Chinese scientists who have established a quantum interface via satellite between ground stations 1,200 kilometers apart. What Mario Kart or Monopoly is for us, quantum physics was for Albert Einstein and Niels Bohr. Although the two physics luminaries were great friends, they repeatedly participated in heated discussions about the subject of whether different fundamental principles apply in the strange universe of quanta than in our ordinary world. One of their main disputed matters was whether two quantum particles can still be in a shared state, even when they are far apart, or whether each particle carries its own individual state. In the first case, which Bohr contended for, both particles would be entangled. In other words, connected to one another regardless of their locations and distances. In this context, any measurement that changes the state of one particle would also have an immediate impact on the state of the other entangled particle. For this case, Einstein supported the idea that both particle states would be fixed from the beginning, and a measurement on one of the particles could impact the other, assuming a message were communicated. And that was exactly the essence of the matter for Einstein. According to the special theory of relativity, such a signal can travel at most at the speed of light, so it would fundamentally take a certain amount of time to travel and couldn't be passed on right away. The bottom line is that Einstein didn't have faith in the phenomenon, which he once famously referred to as spooky action at a distance, and was hence decisively mistaken. In fact, the predictions of quantum mechanics have now been successfully confirmed by experiments in detail. All tests done so far have affirmed Bohr's evaluation that the quantum world involves non-local connections, which is why quantum entanglement is no longer considered an outlandish idea, but a recognized physical phenomenon. Quantum entanglement over 1,200 kilometers, however, the highly intricate tests that provided the proof of quantum entanglement weren't conducted until decades after Einstein and Bohr's deaths. So we can only hypothesize about how the creator of the theory of relativity would have reacted to the pivotal demonstration that Chinese physicists carried out a few years ago. As already mentioned, any change in the state of an entangled photon also causes a change in the state of its partner. So, information can be communicated instantly, or in other words, right away, over huge distances. But this phenomenon too has a significant limit in our natural environment because, in both glass fiber and the Earth's atmosphere, problematic effects ensure that only a few photons arrive at their destination in the entangled state. And so it was that the maximum range of this quantum communication was only 100 km in the run-up to the Chinese trial. But in the vastness of space, the photon pairs are much less disturbed, since the trapped photons travel through the vacuum of space. For most of their journey, they remain entangled, even when sent to two ground stations far apart. Also, the Chinese research satellite Mischius amazingly demonstrated that this theoretical approach also works in practice. It succeeded in sending entangled photons to two receiving stations in China that were as much as 1,230 kilometers apart. Let me know if you'd like me to adjust or clarify anything further. Like this function admirably with regards to the specialized subtleties, the transmission unit of the quantum probe board. The satellite involved a laser, whose beam was directed through a waveguide and a special crystal. Along these lines, 5.9 million entangled photon pairs with a frequency of 810 nanometers were made each second. The entanglements, thus, impacted the polarization condition of the pairs, in basic terms, the direction of their vibration. The satellite's combined telescope dish then assumed the task of sending the two light emissions of laser photons to a ground station. With resonating success, the ground stations were able to receive the satellite's beams without the photons losing their entanglement, even though the pairs were sent to Earth from a height of 500 kilometers and, depending on the position of the satellite, had to travel up to 2,000 kilometers. Another test was the speed of the satellite, since it was continually moving in relation to the ground stations. The transmitting and receiving systems had to follow its movement as precisely as possible. Regardless of this, however, the transmission was powerful enough to read the sent data and thus form the world's first orbital planetary quantum network, a totally new way to approach quantum instant transportation. Did Einstein and Bohr ever envision that their scientific successors would one day venture into space to find the answer to their debate? Well, who knows? What is certain, however, is that, in principle, no quantum instant transportation is required to send quantum data over significant distances. To do this, a qubit, a small quantum data store, can simply be encoded in the direction of the oscillation of a photon, which is then sent through an optical fiber and can, in theory, send the data back and forth between two remote locations. However, because photons are extremely delicate and passing, they are easily lost along the way, and with them, the stored quantum data. Quantum instant transportation can bypass this issue, but, to understate the obvious, it's challenging. After all, it requires two captured particles ahead of time to serve as a resource for instant transportation, and such a resource is generally anything but easy to produce. In this context, the team led by Stephen W.L., Stefan Langenfeld, and Gerard Art from the Max Planck Institute of Quantum Optics considered how it would be possible to complete quantum instant transportation using a more readily available resource, specifically with just a single photon as an auxiliary particle. Published in Physical Review Letters, the series of experiments relied on individual cooled particles and the principles of quantum electrodynamics. The results led to an entirely novel system that uses only a single photon to teleport the spin state of a single atomic qubit to a second atom 60 meters away. The qubit to be teleported was captured in an optical resonator, while the second particle was also captured in a resonator in an adjacent laboratory. To move the data, the researchers mirrored a photon successively at the two resonators in which the two particles were located. The photon flew through an optical fiber connected to the two resonators, and then a measurement of the photon and the spin state of the first particle was completed. Based on these two measurements, a feedback signal was then sent to the second atom, which was illuminated as a laser pulse. Its properties relied upon the previous measurements. With everything taken into account, this method allowed the data to be instantaneously transported from one atom to the next. However, if we let our thoughts run free at this point, another exciting question arises. After all, isn't it possible that quantum instant transportation eventually offers some loophole that could allow the teleportation of humans? To start, it's important to strictly remember that in quantum instant transportation, the data does not travel from point A to point B. Instead, it appears at point B and disappears at point A when you read it. Moreover, the amount of data that can be sent in this way is very limited, usually just a few bits. Another significant obstacle is that one of the two entangled particles must always be brought to the destination first. To teleport data, only when the entangled particles are prepared can the data be shared between the sender and the recipient instantly. In other words, quantum instant transportation requires that the corresponding system be prepared at the destination. If we wanted to teleport a person from a spaceship to the surface of an alien planet in the best Star Trek fashion, it would only be possible if that person's entire set of particles had been measured and their quantum data transferred to entangled particles that had already been sent to the destination in advance. Another barrier is the fact that we humans have the annoying tendency of not being quantum objects. All the particles and atoms in us are subject to so many interactions and disturbances that all quantum superpositions and entanglements would instantly break down. Even in research labs, scientists can maintain these conditions under carefully controlled and protected settings. And, of course, there are the simply practical issues. If we were to genuinely attempt to emulate Star Trek technology, we would need to heat matter to millions of times the temperature of the center of the sun, give more energy to the machine than the entire human race has available, and improve the performance of our computers by a quadrillion times. And to top it off, we'd need to avoid violating the laws of quantum mechanics. Considering all these factors, it's clear to everyone how feasible the realization of teleportation is at present. Even people in the distant future would have to work hard to ever bring such a technology into reality. And if you want us to bring our videos into your world regularly, then simply click the subscribe button. We'd be glad to have you join our community so you never miss another post from us again. We'll see you soon.